Basically, the energy level diagram is going to map out all the allowed states for the electron. And we start off, what's the lowest energy state? The 1s, or AKA, what do we call it? The 100. So we got the 100 of the 1s orbital here. Let's pen this. And then what's next? Do I have a 1p?
No.
Yeah, because L equals 0. If n equals 1, we could have L equals 0, but we can't have L equals 1. And so the next higher energy would be what? Did you guys have this in your notes, right? Yeah. All right. The next one would be the 200. And then here, if n equals 1, then we can have L equals 1 as well. And so we'll get 2, 1. And if L is equal to 1, we have 3 m values. Over here, we only have 1 m value, which is 0. Over here, we have 3 m values. Minus 1, 0, and plus 1. And so we'll have 2, 1, minus 1, 2, 1, 0, and 2, 1, 1, or plus 1. This would be the 2s. This would be the 2p. And so there are 2 subshells in n equals 2. And then we go up to n equals 3. N equals 3 is going to have 3 subshells. You know, the 300 subshell. And then the 3, 1, negative 1, 3, 1, 0, 3, 1, 1. And then we can add another subshell here. L equals 2 is allowed. And so we're going to go from minus 2 to plus 2. And so we'll get 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. That would be it. And so we could just continue this on here. So for example, if I went up to n equals 5, you know, how many orbitals do I have? 24 orbitals. How many subshells do I have? I'd have 5. If n equals 5, I'd have the L equals 0, the L equals 1, the L equals 2, the L equals 3, and the L equals 4. So these are the 3D. 3P. Yeah. And then what's the max here? N equals infinity. All right, so this is their basic quantum mechanical model. The energies here we can get, because the energy is just dependent on n, and it's just minus r sub h over n squared. We figure out all the energies here. And so that part holds true. And so we can see transitions. We see a transition from 3 to 2. If an electron is in the n equals 3 and drops down to n equals 2, it emits red light. When an electron's in n equals 3 and drops all the way down to n equals 1, it emits UV. And the light is characteristic. It's going to have a characteristic wavelength or frequency for that particular transition. And so it'll be very specific for that particular transition. But one of the things here is this, you know, that all these orbitals, let's just look at the n equals 3. All these orbitals are the same energy. And so we call that energetically degenerate. And so the 3s orbitals are the same energy as the 3p orbitals, which is the same energy as the 3d orbitals. But how can that be? Because the s and the p and the d orbitals look so different. You know, how can that be? Well, it just is the same energy. And so when we think about the energy of an electron in an atom, we often think in terms of its distance. So let's take a look at some of these orbitals here. The same thing holds for the n equals 2. So this would be the n equals 3 shell, which would consist of these 3 subshells. This is the n equals 2 shell, which consists of these 2 subshells here.
In Chem 4, wouldn't that 2p is over 2s and 3p is 3s? Is that wrong there?
In Chem 4, no.
That like 3p has more energy than 3s.
Yeah, right. That's not wrong.
It's not wrong?
No, that's not wrong. It's wrong for the hydrogen atom. It's wrong for one electron. This is an energy level diagram for what we call a one electron species. And so this diagram is right for the hydrogen atom. It's right for anything else with one electron. If you have one electron, what's going to happen here is that if we have one electron, all of them are going to look like this. And so if we go to helium plus, what happens is these orbitals get shifted down. And with helium plus, what we're going to see is that helium plus has 2 protons. Well, 2 protons is going to pull in the electron much closer. And so what happens is the 1s orbital shrinks because the electron's being pulled in closer, and it goes down in energy. And so essentially the same pattern, it's just the relative energy. It's different for one electron species. And so we have to understand the one electron species in order to understand the multi-electron species. So let's go and take a look at some of these orbitals here. Try to better understand why so if we look at the general shapes of these, this would be a 3s, let's say. Actually, this is not a 3s. There should be nodes and other stuff. This would be 3D, so this is not to scale. But you know, the general shape of the 3s looks like this, 3p, 3d, like this. When we look at the energies of these particular orbitals, we can think in terms. So this is a 1s orbital. So let's look at the 1s orbital right now. I'll look at it in more detail. So how does a 1s orbital differ from like say a 2s orbital? A 1s orbital, one way of thinking about it is like the bird analogy. You know, you can think of the nucleus as being the nest here. And then the bird, you know, the bird is going to seek out food, you know, out from the nest. And so as the bird seeks out food, maybe it's here in one instant of time. In the next instant of time, let's say if I pinpoint the bird here, so I'm watching the bird, can I predict, like say, I want 1 minute later, I want the precise position of the bird. You know, and so can you predict in 1 minute later where the bird's going to be exactly? Do you think that's possible? It's not possible. I don't think it's possible. What about 10 minutes later? If I know the bird's here, 10 minutes later, do I know exactly where that bird is? No, there's no way I'm going to know where that bird is. However, if the bird doesn't have too much energy, then what I can say is the bird is going to be kind of close by the nest, right? It doesn't want to go too far away. And so what I can say is this. I can say, you know, the chances of finding the bird are going to be much higher near the nest because it doesn't have to have too much energy to get out. But let's say the bird is really energetic. If the bird is really energetic, then it can go farther from the nest and seek more food. And so the bird analogy is twofold here. One, the bird analogy illustrates something like the Heisenberg uncertainty principle. Let's say I pinpoint an electron here. Okay, tell me where that electron is going to be 1 second later. Can you tell me exactly where that electron will be 1 second later, or maybe 2 days later? Do you know where that electron is going to be? And so this is the Heisenberg uncertainty. We don't know exactly where that electron is going to be. You know, we pinpoint the energy is here. We have an idea, you know, it's not going to stray too far from the nest, but it is possible it could. You know, maybe it is possible that bird can go kind of far. Well, the same thing with electron. Now, the other thing is, this is quite different than the Bohr. You know, the Bohr model, did it incorporate the Heisenberg uncertainty principle? No, it didn't, because in the Bohr model, what we have is this. In the Bohr model, we have an electron, and the electron is orbiting around the nucleus. So if we pinpoint the electron here, then we can predict, you know, based on its energy, its speed, where it's going to be 1 second later. 1 second later, it's going to be, we can pinpoint that. It's like the satellite. If you're, if you have a satellite orbiting the Earth, you know, can you tell me where it's going to be 10 minutes later? Yeah, you should, because it's following a simple trajectory around the Earth. You should be able to tell me, well, what about the Heisenberg uncertainty principle? Doesn't the Heisenberg uncertainty principle apply to all matter? It does apply to all matter. But when you look at the Heisenberg uncertainty principle, the Heisenberg uncertainty principle says that uncertainty in X times uncertainty in the energy is going to be greater than or equal to, the smallest it can be is, what is it, h over 4 pi? What is h? H is on the order of 10 to the minus 34, right? Planck's constant. And so actually these uncertainties are actually quite small. So if you're looking at something like a satellite, let's say there's an uncertainty in the position of the satellite of 10 to the minus 10 meters. Is that anything? Is that really, 10 to the minus 10 meters, that's like the size of an atom. You know, if there's uncertainty in that, it's nothing. It's negligible uncertainty. But when we're thinking about an electron, the uncertainty is quite big, you know, compared to an electron. And so for macroscopic objects, the Heisenberg uncertainty applies, but the uncertainties are so small that they're negligible. For tiny objects like this, so something like the Bohr model, there's no uncertainty here because we know, okay, it has this energy, it's moving this fast, it has this radius. What was the first Bohr radius? The first Bohr radius. In angstroms or picometer?
1 angstrom.
The radius.
Oh, radius.
Yeah. Diameter is about 1 angstrom. What's the radius?
So it'd be roughly around 50 picometers. If
They're
it's,
roughly around 50 picometers.
Yeah.
What did I tell you guys? 0.54 0.54 angstroms, or 4.5 is too small. 0.54 angstroms, or 54 picometers. And so we know, okay, the Bohr radius is 54 picometer. We can pinpoint the electron, but we know this is wrong because of the Heisenberg uncertainty principle. The Heisenberg uncertainty principle is like this. This is the way to think about it. And the way to think about it is not like Bohr. Actually, this is what the drawing was here earlier. Let me erase it. But it'd be like the bird. And so let's say the nucleus is the nest for the bird. And we're going to try to pinpoint the electron, but actually we have uncertainty. We can pinpoint it, let's say, but we don't know where it's going to be next. Because if we pinpoint the electron, do we know how fast it's moving and what direction it's moving? We don't. Because that would be energy, how fast it's moving and what direction. This is called velocity. And so the electron, let's say, is here. Electron's here. Okay, so we pinpoint an electron. We don't know where it's, in what direction it's moving because the act of observing the electron, is going to change its trajectory. And so here, pinpoint there, and then here. And so we start pinpointing the electron, and we see it's kind of like the bird, you know. We don't know where sometimes it's far out here, but most of the time it's nearby. Lower energy bird, not a high energy bird. And so most of the time we pinpoint it, it's going to be close to the nest. And as we get farther from the nest, it drops down. The probability drops down. And so that's what this peak is showing. This peak is showing, well, this is the wave function. And what we do with the wave function, psi, the psi is the answer to the question of what the allowed state of the electron is. And so this is allowed. Here's a contour map. This is the contour map here, which it rises up in elevation. Here's psi squared. Psi squared is the probability. We can see the highest probability is going to be right next to the nucleus. As we get further and further away from the nest, the probability is going to drop. Actually, the probability doesn't go down to 0 until we hit r equals infinity. But well before we hit r equals infinity, the probabilities drop very close to 0. In fact, when we look at this, 95% of the probability can be contained in a relatively small volume. And that small volume is given by the sphere here. This is the 95% probability boundary. And so that's what we have. And so we can do that here. We can capture 95% of the dots, like this. So 95% of the dots will be in here, 5% will be outside. So this is 95% boundary. Now let me ask you this. We know that Bohr model's wrong, right? But some aspects aren't. So for example, the energy is the same equation that we get from quantum mechanics. But what about this 54 picometers? Is that completely wrong? Or is that related to something in quantum mechanics? So for example, if I have the 95% shell here, is this 95% shell, is this at 54 picometers? Is that at 54 picometers? No, it turns out no, it's not. Do you know where that 54 picometers comes from the Bohr model? I'm sorry?
Is it because the app is also about the force between the electron and the nucleus?
Yeah, right. This electron is going to have an energy, and that 54 picometers comes from this. The 54 picometers is like if you average out the energy here, that is, you know, if you take this collection of positions and you say, okay, I'm going to take the average of all these positions and give it one effective position. And so you take the ones that are close, the ones that are far, the ones that are close low energy, the ones that are far high energy, and you average out all those positions, you come out with 54 picometers. And so 54 picometers is what we call the effective distance that the electron is away from the nucleus. And it's not here. And so 54 picometers in quantum mechanics equals the effective distance. Electron, for the electron. And the effective distance is going to impact its energy. The further away it is, the higher energy that electron must have. The closer it is, the lower energy that electron must have. And so this is like saying, okay, you know, this bird has a certain amount of energy, and based on, you know, it's the pattern and this distribution, we're going to say that, you know, effectively the bird is this far away from the nest. So where does that effective distance come from? How do we come up with that? And so let's take a look at the 1s orbital. And so this would be 1s orbital. There are different ways of writing this out. We could call it a 1s orbital, or we could call it a 100 orbital, or we could call it a psi 100, or we could call it a psi 1s. Okay, this is a loud state. Now, psi squared is what? Psi squared is the allowed state squared, but why squared? We square it to get the
All those other
probability. So chi-squared is the probability. The highest probability is going to be where? The highest probability of finding the electron is right at the nucleus. And then the probability is going to drop. The further away we get, the lower the probability. And so what I'm going to ask you is this. What is the most probable distance the electron is away from the nucleus? If I think about the most probable distance the electron is away from the nucleus, in other words, let me ask you, what is the most probable distance that the bird is away from the nest? Would you say the most probable distance is 0? I might say 0 because the highest probability is right at the nucleus. You look at this peak, the highest probability is right at the nucleus, so this is it in 3 dimensions. I'm going to see the greatest density of dots right at the nucleus. And so is that the most probable distance for finding the bird? It turns out that that's not the most probable distance. In order to figure out the most probable distance, yeah, it's too low. The most probable distance is given by the RDF. The RDF is called the radial distribution function. And so in order to determine what the RDF is, we do this. We divide the volume around the nucleus into hollow spheres. And so this would be the first hollow sphere. The next hollow sphere is going to have the same thickness as the first. It's like, this would be like an onion, where each layer of the onion has the same thickness as the previous layer. Even though my drawing's not so great. Trying to draw that out. And so I divide up the volume around the nucleus into equal spheres. Spheres, hollow spheres of equal thickness. All right, then in order to find the most probable distance, we look at each hollow sphere and we count the number of dots in each hollow sphere because the dots give us an idea of where that electron is in that instant of time. And see, we see the most dots are right at the nucleus. And so right at the nucleus, we have the greatest concentration of dots. But the situation is the volume. If you look at the volume of the sphere, this sphere has the smallest volume out of any of them. If we look at the sphere with the greatest volume, that would be at near infinity or at infinity. But as we go farther and farther away, this sphere with equal thickness, like this, the volume of this hollow sphere is much greater than the volume of this hollow sphere. But are there any dots there? Maybe there's one dot or a few dots, but there's not much. And so what we have to do in a radial distribution function, we're looking at how the distribution spans out radially from the nucleus or nest. And we do that using these spheres. And when we look at the spheres are going to behave like this. The spheres this is the volume. And so the first sphere is the smallest volume, but as we get further and further away from the nucleus, the volume of the spheres increases. And so what we're going to do is, which of these spheres do you think is going to have the most dots? Well, it's going to be a sphere that maximizes the concentration of dots while maximizing the volume. And so we're going to maximize two functions. We're going to maximize the concentration of the dots. That means we want to get the purple curve as close to the nucleus as possible. But we also want to maximize the volume, because the greater the volume, the more dots we can capture. And so we want to maximize the blue curve, right? Like this. And what results is this. What results is a curve that looks like this. Here, where we see a peak here. And this peak is going to be the best compromise. So we don't want the smallest volume, because when we count the number of dots, even though it's highly concentrated, it's not as many as we go out here. We go out here, we got a much bigger volume, and we can capture more dots. And then as we go further and further away, the dot density decreases. And so this here is the most probable distance. The electron is away from the nucleus. The most probable distance isn't right at the nucleus. The most probable distance is a little bit off from the nucleus. Do you know where that is at? This is at 54 picometers. Here. And so this is where that comes from, the 54 picometers. And this is what we call the effective distance. The effective distance is, if we imagine an electron here and calculate the energy of that electron here using physics, then we would get the whole, the same energy as if we calculated the whole distribution and then averaged it out, right, to how many dots we got. Okay, so this is for the 1s orbital there, or the 100 orbital. All right, so that's the radial distribution function. Now, what happens if I go to a, this is a 1s. What happens if I go to a 2s orbital? So let's take a look at a 2s orbital here. Let me erase this. Here. If I look at a 200 orbital, and I look at the psi, like this, the psi, well, n equals 2 is going to have how many nodes? N equals 2 has how many nodes? Internal nodes. How many internal nodes does n equal 2 have? N equals 2 has a total of 2 nodes, but one of those is a node at infinity. So a node at infinity, everybody has a node at infinity, so let's forget that. Let's just talk about the internal nodes. It has 1. And so when I look at psi, what I'm going to see is I'm going to see positive amplitude, go to negative amplitude, and then converge that way. So this is positive, that's negative. This is why probability psi squared, because do we want negative probability? Hey, what's the probability of finding an electron? Negative? Does that make any sense? It doesn't make any sense, so that's why this is going to be squared. This is symmetric here. I'm not drawing the other half. And so psi squared is going to look like this. Psi squared, we're going to go like this. Here. And so we'll have a node here. This would be a node, an area of 0 probability. Since we lose the amplitude information, we'll label this plus, we'll label this minus. And so instead of doing the color coding thing, we'll just use the symbols. So we can see the 2s orbital here. There's one internal node. This blue is the positive amplitude. The red is the negative amplitude. And the outer surface of this shell is what we call the what boundary? The 70% boundary? This is the 95% boundary, meaning there's a 95% chance we'll find the electron inside this volume and a 5% chance we'll find it anywhere else in the universe. And so that's it. Well, take a look. The 95% boundary has grown a lot bigger because a 2s electron is much higher energy. So this one is a higher energy bird or whatever, and it can fly further from the nest. But you know, the chances of it flying way out here are pretty low. It doesn't have that much energy. Well, anyway, we could do the same thing here. Where do you think the most probable distance is? The effective distance of the electron. Do you think the most probable distance is at the point of highest probability? You know, it seems to make sense. The most probable distance should be at the highest point of probability, right here, but that's not the case, because what we're doing is we're doing a radial distribution. And so we're going to slice up the volume around here, and then what we're going to see is, we're going to see, even though this has the highest probability, the volume is quite small. And the volume is going to increase like this. Volume increases. And so what we got to do is we got to maximize both functions. When we maximize both functions, what does the RDF, the radial distribution function for 2s electron, look like? Can you draw it? Guess, why don't you just try to draw it and see how close your drawing comes out to the actual. Okay, and do that.
Or maybe they don't cancel out, maybe the whole distance is down here. You just erase it and then left.
This whole shelf stuff was mainly because of how to that.
And it makes sense because that's where the volume, that's where it's supposed to volume.
No, Korean. You should try Korean.
I get what you're saying.
We're just seeing like with the highest.
Do what?
It shows you that
Yeah.
we're just seeing them.
Right, it was the same thing, right? So it would be like right here.
Where are you trying? I'm trying where? Okay, one time. Your power changes every 5 years.
Yeah.
So you were saying about this too.
Minor changes.
Yeah, like you become more.
So do you have the RDF? Does somebody have it?
Would it,
Just describe it to me. I'll draw it.
well, wouldn't it be where, so you erased the previous graph, but the negative was, the wave was kind of inverse, so would it be from below there to the top of that one? Because that's the closest to volume wave. So in psi, not squared, and just psi alone, it dropped down negative and then it came back
Okay.
level.
Okay.
Does that make sense?
Yeah, except the negative, the negative is, when we're looking at an electron, the electron can be either in the positive or the negative lobe. And so the negative is not going to
It's not going to affect it.
not going to affect it, because what we're doing is we're trying to maximize probability. Probabilities are always positive, and so the lowest probability you can have is 0. You can't go lower than 0. And so what we're trying to do here is we're trying to maximize the black and the purple. On the one hand, we want the biggest volume, but if we have the biggest volume, the probability is next to 0. And so here, yeah, we got a great big volume, but there's no dots. And so as we go in closer and closer, the density of dots grows. So if we're right next to the nucleus, wow, we got a lot of dots there, except the volume is extremely small. And this volume of dots, the volume, can you guys visualize this concentric sphere thing that I'm talking about? If you got calculus, It's much easier. If you have calculus, then you're used to slicing things into little segments. But if you didn't have calculus, that's okay too. You don't need calculus to figure this out. And so this whole idea. See what's happening here. Did I get logged out? Try it again. Oh, okay, it's working. So our book talks about it in problem number 110. So here you can think of, in terms of the volume of it, if you want to actually calculate the volume, given the volume of a sphere is 4/3 pi r cubed, show that the volume dV of a thin spherical shell of radius r and thickness dr is 4 pi r squared dr. And so this is the volume of that shell. Yeah. This exercise can be done easily and elegantly by using calculus. It can also be done without using calculus by expressing the volume of a thin spherical shell as a volume difference, of two spheres, and simplifying the expression. So this is another way of figuring out the volumes. If you want some numbers, you can put. But essentially, it's going to look like this curve here. As r increases, so does the volume. Increase is nonlinear. But what we're trying to do is we're trying to maximize two functions. Have you guys maximized two functions? Like, if we try to maximize the two functions, then what it's going to look like is going to look like this. There's going to be a node here, zero probability. And so even though the highest probability is right at the nucleus, the most probable distance, or the effective distance, is going to be a bit farther from the nucleus. And in fact, this is going to be farther than the 1s. The 1s is closer. The 2s is farther. But when you look at the probability, it looks like the 1s and the 2s are right on top of the nucleus. Does that make sense? And so here, this would be the effective distance. Well, this should be like the second Bohr orbit. The second Bohr orbit should be around here. Does that make sense? That makes sense in the sense that the energy equation holds. And so if we treat all those positions and get an effective average, this would be it right here. Okay, the RDF. And so let's take a look at those two here, RDF. So I didn't want to show you 6 RDFs right at the start, so this is why we just started with 1 RDF. Do you recognize this RDF? What is that? That's the 1s orbital. Where's the most probable distance? The most probable distance is going to be at that peak there, which is roughly at are you sure? We were not supposed to use angstroms because Petrucci said 54 picometers. But if you look at the units here, and this is a problem. Did Petrucci give us units here? No. That's a terrible mistake. You're not supposed to do that. You're always supposed to have units on the axis. If you don't have units, we have no idea what those numbers are. But you know what? I know what the numbers are because RDFs are typically with units of with angstroms. Yeah. So RDFs are typically with units of angstroms, and right off I knew this was angstroms because I've seen lots of RDFs, right? Lots, way more than this, because RDFs are used for a lot of different things. And it's odd that, on the one hand he tells us to abandon, on the other hand he uses it. But it's okay. Overall it's a good book. So that's it. This is the 1s, so the effective distance is here. Now let's go to the 2s. Do you see the 2s? 2s, you know, we expect a bigger peak here, but the peak isn't so big here because of the... Why is the peak so small here near the nucleus? Because of the volume, the small volume. And the peak maxes out around here. Do you see that? And so for a 2s orbital, the effective distance is, let's say, around here, right? And this is the most probable distance. But for a 2p orbital, this is the 2p orbital. 2p orbital is a different shape, right? And 2p orbital has a node right at the nucleus. There's a planar node. Take a look at the 2p orbital and compare it. Look at the most probable distance in a 2s orbital. Looks like on the other side of 5, right here. On a 2p orbital, it looks like it's closer. So if the electron is closer to the nucleus, that means it has lower energy, like the bird. If the bird, you know, if the electron ventures further and further out from the nucleus as its most probable distance, then it's got higher energy. So looking at this, it looks as if the 2p orbital should be lower in energy than the 2s orbital, because the 2p orbital is effectively closer to the nucleus. Is that right? It can't. That's not right, because didn't I just tell you that the 2s and the 2p are the same energy? If they're the same energy, then they both must have the same effective distance. And so what we see here is a difference. Both of these have the same effective distance, but they have different probable distances. How's that possible? How it's possible is because of the shape. And we have to start thinking about this. We have to start thinking about three-dimensional shape in terms of different words, like spherical symmetry, you know, isotropic, anisotropic. Have you heard of those terms? Isotropic versus anisotropic. Isotropic means it's the same in all three dimensions. So anisotropic means it's different in three dimensions. And so an example of isotropic versus anisotropic would be electrical conductivity. If you have a piece of gold, it conducts electricity in any direction the same. Right? But if you have a piece of graphite, let's say a crystal of graphite, then it's anisotropic. Because graphite, did you know graphite's an insulator in one direction, but a good conductor in two other directions? That is, it has a certain asymmetry versus symmetry to it. And so when we're dealing with s orbitals are all spherically symmetric. But now we have a p orbital. A p orbital is not spherically symmetric. And so this is how the effective distance is the same. The effective distance is the same like this. So if we look at the nucleus here, and let's draw out a p orbital. The p orbital, the most probable distance is closer. So let's say the most probable distance is here and here. Is this isotropic or anisotropic? Well, is it the same? No matter if you're standing on the nucleus, no matter in which direction you look, it looks the same. Is it? Because you know what this line represents? This boundary represents, what was it? The 85%? That's the 95% boundary. And so that means there's a 95% chance of finding an electron inside here. What's the chance of finding it outside? 5%. And so when you're looking at this, and you're observing the electron, let's say you were on the nucleus and you could observe the electron, you'd see dots, the highest concentration of dots, but there are going to be some dots out here. Not many. The highest concentration dots will be inside those, in a very small can. And so in this sense, it is not, it's not isotropic, because you're looking here, and we have the most probable distance here in three-dimensional space and here in three-dimensional space, but this does not go around. That is, this is not spherically symmetric. Okay? Whereas an s orbital is. An s orbital, if we superpose an s orbital here, so let's just draw the 95% boundary for an s orbital. And so if we draw an s orbital here, then we look at the most probable distance. The most probable distance for an s orbital is a little bit farther. And so if I look at the most probable distance for an s orbital, it's like this. So there are two things that can be done. If you take in physics and electricity and magnetism, you could do this. You could figure out the energy based on this distance and limiting it to this volume here and this volume here. You could do that. Or what you could do is you could take this and then normalize it over the sphere. And so this is like, let's say you're putting fertilizer in the garden. You put a whole bunch of fertilizer here and a whole bunch of fertilizer here, but now you got to spread it out over the entire garden, right? When you spread it out over the entire garden, it's going to weaken. Is it going to be as concentrated? No, it's going to be weakened in that sense. And so if we normalize the 2p over 3 dimensions, rather than, not 3 dimensions, this is already 3 dimensions. If we normalize it over spherical symmetry, like this, then the 2p orbital will have the exact same effective distance over a sphere as here. And so it turns out the strength of electrical interaction here is going to be the same as here. Does that make sense?
Yes.
And therefore, the 2s and the 2p are the same energy. They're the same energy even though they have different shapes, even though they have different RDFs. The 2s and the 2p have different RDFs. Even though they have different most probable distances, their effective distance is the same because we normalize it over the three-dimensional sphere. Does that make sense? There. And so the same thing happens. If you look at the 3s and the 3p and the 3d, let's take a look at the most probable distance. The most probable distance in a 3s is here. Okay, look at the number roughly. For 3p, it's here. For 3D, it's here. Are they the same? No, they're not the same. In fact, the 3D is actually quite a bit closer, right? But then when we look at the shapes of these orbitals, let's look at the 3D. We have that. When we look at it, these are not isotropic. That is, these don't have spherical symmetry. And so what we have to do is we have to normalize it over the sphere. And when we normalize it, then the 3s, the 3p, and the 3d will all share the same effective distance from the nucleus. Does that make sense? Okay. Good. Okay, this is the reasons why, Peter was asking, aren't the energies different? No, the energies are exactly the same. The 2s and the 2p have the same energy because they both have the same effective distance. And the 3s and the 3p and the 3d all have exactly the same energy because they all have the same effective distance from the nucleus. And so this is why they're all the same. The energies are all the same.
Is this still specific for the hydrogen atom?
Yeah, this is still specific for the hydrogen atom.
Okay.
All right, now when we see, okay, the effective distance is the same and the energy is the same. What's different? Obviously, the shapes are quite a bit different. Shapes are different. What else is different? Well, let's take a closer look here. Their RDFs are quite a bit different. Let's look at the 3s and the 3p and the 3d. Yeah, the most probable distance is the same. No, the most probable distance is different. The effective distance is the same, right? But there's something else that's different here when we look at this. And that something else is this. This is something that we're going to look for. You know, as this, we got this hump here, you know, a couple of humps, depending on how many nodes we got. For n equals 3, we have 2 nodes. Here you can see the 2 nodes. Here, there's 1 node here and 1 node here. Here, you can't see the nodes because they're sliced along planes. But when we look at this, there's one other thing we should notice, and that's near the nucleus. What we want to see is this. If you look near the nucleus, these 3 orbitals are going to have a different probability of being near the nucleus. When you look at the 3D, is there much of a probability of finding that 3D electron near the nucleus? No. If you look next to the nucleus, there's very little. Whereas a 3s, you see this little blip here. That's significant because that little blip means that there's some probability of finding the electron very close. And in fact, there's good probability compared to this. We have a name for that. If there's a decent probability of finding the electron closer to the nucleus, that is, this 3s electron can sneak in close to the nucleus, whereas a 3d electron can't really sneak in close to the nucleus. And look at the radial distribution function. We have a name for that. Do you know what the name is? The name's given here. The name for that is penetration. And so the title of this slide is penetration. When we're thinking about penetration, we're looking at how close. The most penetrating orbital out of all these is which one? It would be the 1s. The 1s is going to have the highest penetration. And the 2s is pretty good, but the s orbitals are good. How about the p orbitals? The p orbitals are next, and the d orbitals are the least.
But if you normalize the effective distance, what effect does that have on the probability?
It doesn't have any effect on the probability.
So the probability is
Because, yeah, that effective distance is factoring in this probability here of being close to the nucleus. We're factoring in the probability of being close to the nucleus and factoring in the probability of being far from the nucleus to get the effective distance. And the effective distance is going to come from that distribution here. And the same thing here, and the same thing there. And when we kind of average these out, they come out the same, right? But the distribution looks different, you know. Even though the average is the same, the distribution, it's like that 67%. You know,
so a d orbital electron would still never be able to get as close to.
It would never be able to get
S.
as close
Okay.
to the 3s. All right, and so what we need to know is that this s orbitals are much more penetrating than p orbitals than d orbitals. And this is why the Bohr model failed. The Bohr model failed because they couldn't interpret multi-electron atoms. For single electron, it's no problem. For single electron, we have this situation where all the orbitals are the same energy. But once we start putting other electrons in there, then we have something else pop up, and that something else is called shielding. And so let's talk about shielding really quick here. We'll take a break. Shielding is like this. If there's only one electron here, let's say I put an electron here. Nucleus is here. What's the charge that electron sees? The charge the electron sees is plus 1. If that electron moves to here, did the charge on the nucleus change?
Nope.
No, it's still plus 1. And so what we say is that one electron species has no shielding. Because if I all of a sudden I put another electron here, is this electron still going to see a plus 1 if there's another electron here?
No.
No, because what's going to happen is this electron inside here is going to block some of the nuclear charge from this electron here. And that's what we call shielding. But what are the chances that this electron might sneak around this electron and get close to the nucleus?
Slim.
Is it possible? Is it possible for this electron to, in one instant of time, sneak around this one and get close to the nucleus? Is that possible or impossible? For 3s. Is it possible
It is possible.
that a 3s can sneak around? Let's put the 1s electron here. Let's say in one instant of time it's at this distance. Is it possible for the 3s electron to sneak around that 1s and go right to the nucleus? It's possible. That's called penetration. And so 1s is blocking, that's shielding, but the 3s can penetrate around the 1s and see more of the positive charge. And electrons are negatively charged, so that's what it wants to do. And so what we have to think about now is this. If we're looking at an electron here, and we have a nucleus here, and let's say the nucleus is plus 10, because we've got 10 protons in there. The nucleus is plus 10. If I throw an electron here, what's that going to do? It's going to block it. And so Z, this is what we call Z. And then we have Z effective. Z effective is the charge that it actually sees. Well, the charge that it actually sees is blocked. It's blocked because of shielding. And so Z effective is, well, if this is plus 10, that's minus 1. You know what it is? Plus 9. If I throw in another electron in here, the 2 electrons blocking, it's going to go to plus 8. Let's go 3 electrons. It goes to plus 7. Well, what if the electron's not there? What if I put the electron out here? If the electron's out here, is this one shielding? No. But what if the electron's here, right next to it? Is this one shielding?
Right next to it.
Right next to it? A little bit, but not much. And so this is what we say. We divide this up into shells here. Inner shell electrons block nuclear charge effectively. Same shell electrons aren't so effective at blocking nuclear charge. We can get all detailed on this if we want. If we want to get quite detailed, we can come up with this. This is
How does an electron penetrate if an orbital is full, though? Say the 1s orbital is full.
how does it? If the one, it doesn't matter. If the 1s orbital is full, here. Actually, I'll just draw it. If the 1s orbital is full, the 1s orbital is going to look like this. We'll put 2 electrons in here. 1s orbital is full. Does that mean a 3s orbital? Does that mean the 3s orbital is blocked out of this volume? No, because the 3s orbital is a different energy. And so it can occupy this volume no problem. So 3s orbital is going to look like this. Sure. So the electron here is in a 3s. Unfortunately, this electron is going to be pretty well shielded, right? But this electron, there is a small probability that this electron can be here, in which case it'll be less shielded, right? Because it's getting around there. But it's still small. And so having this full doesn't impact this at all because it's totally different energy. You know, the effective distance is going to be way out here because it's a higher energy electron. That's all. Also, this is 3s. The 2s electrons will also shield. What do you think is better at shielding, the 1s or the 2s? The 1s. And so we could figure this out quantum mechanically, but a person named Slater, John C. Slater, came up with Slater's rules. Slater's rule, this is not Slater's law, it's Slater's rule. And so let's see. We have seen that the wave functions of hydrogen-like atoms contain the nuclear charge Z for hydrogen-like atoms and ions, but modified through equation 9.3 to account for the phenomena of shielding or screening. Shielding and screening is the same thing. In 1930, John C. Slater devised the following set of empirical rules to calculate a shielding constant for designated electron in the orbital ns or np. And so these are called Slater's rules. Why didn't he call them Slater's law? It's because these rules that there's it's a little less quantitative aspect to that and more exceptions. So these are ways of estimating how much shielding it is. And so we write the electron configuration like this. We write it like this because of this. We write it in terms of shells. And the reason we write it in terms of shells, these kind of shells, is because of this. If an electron is in the same shell, it's not a very good shielder. If an electron is in an inner shell, it's a much more effective shielder. All right, electrons in the groups to the right contribute nothing. So if an electron is out to the right, is it going to contribute anything to the shielding? Nothing. All the other electrons in the same shell shield the designated electron to the extent of 0.35 each. So I asked you, is this electron going to shield very well? The answer is no. But it does shield a little bit. We'll lose 0.35 of Z. And so sometimes this electron will move in front and block it. And so a third of the time we're going to say it's going to be blocking it. 2/3 of the time it's not. And so this electron in the same shell or the same end will reduce the nuclear charge by 0.35. All electrons in the n-1 shell shield to the extent of 0.85 each. So the n-1, so this is the n shell. So if I go to the n-1 shell, then I have to reduce Z by minus 0.85. And so if this is the 3s, then this would be the n equals 2 electrons. All electrons in the n-2 shell or lower shield completely. And so any electrons in these innermost shells are going to be -1. And so in this case, if this is n equals 3, then that would be n equals 2, n equals 1. But if this is n equals 5, this would be n equals 4, this would be n equals 3, 2, and 1. But we don't have to pay attention to these numbers. You don't have to memorize these numbers. What we're going to say is we're just going to come up with a crude qualitative comparison. What we're going to say is that inner shell electrons are very effective at shielding, between 1 and 0.85, right? Same shell electrons are poor at shielding. So this is homework from number 69. This isn't actually in the book. It's just in the homework. And so what you can do is you can use these Slater rules to calculate. For example, you can calculate Z effective for valence electron in oxygen. So you could see, how much of that nuclear charge is a valence electron in oxygen seeing. Or you can calculate Z effective for the 4s electron in copper. You can calculate Z effective for the 3d electron, etc. by using Slater's rules, if you want. And Slater's rules, these are empirically derived, so it's pretty close to the actual theoretical number that we see. All right, so what all does this have to do with everything? What all this has to do is this now. If we start putting electrons in here, let's say there's some electrons in here. Actually, each orbital holds two electrons. Then the 2s orbitals, even though these are the same effective distance, the 2s and the 2p, it turns out that the 2s orbitals are more penetrating than the 2p. And so even though these are the same effective distance, the 2s are more penetrating. So the more penetrating means that they're shielded less by the 1s electrons here. So if I have an electron here, it's going to be lower in energy than an electron here. Electron here will be higher in energy because it's less penetrating. And so what we see is for multi-electron species, whenever we have more than one electron, we have to worry about penetration and shielding. And so for multi-electron, what happens is these energies split. They're no longer the same. And so the 2s and the 2p are different. And the same thing happens here with the 3s. The 3s are lower in energy, the 3p are a little higher in energy, and the 3d are much less penetrating, much better shielded, and so those are going to be even higher in energy. Now, a weird thing happens here. A weird thing happens in most atoms. What happens is the 4s. 4s is much more penetrating than the 3d, and so the 4s actually ends up being lower in energy. Actually, the 4s ends up being lower in energy than the 3d here. But the normal pattern is now, in the hydrogen atom, in a one electron species, the energy only depended on n. And so when we looked at the equation for energy, it only depended on n. In a multi-electron species, the energy depends on n and L. Primarily on n, because there's going to be a big jump. So n equals 1 to n equals 2, big jump. And then secondarily on L. As L grows bigger, we go from L0 to L1. L1's higher in energy. In other words, a p orbital is a higher energy than s orbital because it's less penetrating. A d orbital is higher than a p orbital. And so it's going to go like this, s, p, d, etc. These are going to go higher in energy as we go across for a given n. All right, let's stop here. We'll take a break and then talk a little bit more.